Hey math kids, let's talk about this last example with acceleration. So a train is initially at rest at a station. It begins to accelerate according to this function. So it's a of t is equal to 1/2 e raised to the negative t over 100, and that's measured in meters per second squared. Once again, your book writes it like this, but just know that this thing is the same thing as this thing. Okay, so first they want us to find velocity. And so to go from acceleration to velocity, we need to take the integral. Okay, so we have 1/2 e to the negative t over 100 dt. Okay, and when we do this, the 1/2 just comes down. E to the x, or e to the t, is just itself. And then we need to divide by the derivative of the inside. And so the derivative of the inside is just going to be negative 1 over 100. But if we flip that upside down, we get negative 100 over 1, because dividing and multiplying by a reciprocal are the same thing. And then we want to do our plus c on the outside. Now we can simplify this constant to negative 50 e to the negative t over 100 plus c. And so this is our velocity function. Okay, that's what they wanted. And then they want us to sketch the graph. So if we have a negative, so let's go through a little thing real quick. So e to the x would just look like that, something close to that. Now this negative out in front is going to take every y value, flip it negative, so it's going to look like this now. And then this negative up here is going to take every x value and flip it. And so now it's going to look like this. And so that's the general shape that we have. And then we can, with other things that are going, we can change the shape. And so if we plug in a 0, for example, we can, let's see, we can graph it, and it's going to have this general shape. Now, in order to graph it correctly, we need to know what c is. And so in the problem, let's see, does it tell us the initial? The train is initially at rest at the station. Okay, so what that means is if we plug in a 0 for v of t, and we plug in a position value of 0, then we can solve for c. So 0 over 100 is 0. Negative 0 doesn't really mean anything. It's just 0. And so this is like e to the 0. E to the 0 is 1. So we have negative 50 times 1. And that's really just negative 50, so we don't need that. We add 50 over here, and so we see that c is equal to 50. And so I'm just going to replace that c value with a 50. Okay, so we're going to shift this shape up, and if we, if you graph it on a calculator or whatever, it's going to look roughly like this. Okay. Now, how long will it take for the train to reach the speed of 40 miles or 40 meters per second? So we want to look at 40 meters per second. And so we're just going to set our velocity equal to 40. And so I'm going to take this function, set it equal to 40. And we just need to solve that for t. So I subtract 50. It gives me negative 10 is equal to negative 50 e to the negative t over 100. And from there, we need to divide by 50. That's going to be 1/5. To get rid of an e, we need to take natural log of both sides. So we get natural log of 1/5 is equal to negative t over 100. We multiply both sides by 100. So we get 100 natural log 1/5 is equal to negative x. So we can just bring that negative over on this side. And we end with that value for x. Now, if we just plug that, into a calculator, we can get an answer for that, and the answer is going to be 160.9 seconds. So after almost 161 seconds, that's when we're going to get up to 40 meters per second for our velocity. Okay, we have one more. How far will the train travel in this time? So the train does not change direction. Like obviously, like right here, we don't see the velocity function crossing the x-axis. And so all we need to do is plug in, use these 2 points. So we have this thing and then 0. So I'm going to write in the exact value. So 100 natural log of 1/5. And then we're just going to take the integral of the velocity function. So this one right here, which is negative 50 e to the negative t over 100 plus 50. Okay, and so when we take the integral of that, we get, bring down the 50, negative 50. Since e to the x is its own antiderivative, we do that, and then we need to multiply by the reciprocal of the derivative. So we get negative 100 that we times that by, and then this one just becomes 50t with the antiderivative. And so we multiply those together, we get 5,000 positive e to the negative t over 100 plus 50t. We're going to evaluate that from 0 to negative 100 natural log of 1/5. All right, almost there. So we need to plug this in, and so just plugging in this value, I'm going to get 5,000 e to the negative 100 natural log of 1/5, and that is all over 100 plus 50 times negative 100 natural log of 1/5. Okay, now the other piece, when I plug in 0, if I plug in a 0 here, this just becomes a 0, and so e to the 0 is 1, and so I just get 5,000 plus, if I plug 0 in, that's just a 0. Okay, so I'm hoping a bunch of stuff cancels or whatever. So these negatives cancel, these 100s cancel, e and natural log cancel, and so it's really just 1/5 times 5,000, and so that's just 1,000. Okay. This one right here, we get negative 5,000 natural log of 1/5. That's those minus 5,000. Okay. Now, if we do the 1,000 minus the 5,000, we end up with negative 4,000 minus 5,000 natural log of 1/5. And if we plug that into a calculator, we're going to end up with about 4,047 meters. If you need additional help, please come to Math Lab. Until then, calculator.